So the question is most stones removed with same row or column. Now, a stone can be removed if it shares either the same row or the same column as another stone that has not been removed. Given an array stones of length n, where this is represents the location, return the largest possible number of stones that can be removed. And which stones can be removed if it shares either the same row or the same column as another stone that has not been removed. So this is what we are going to check at the end. But we will start with the question and we will use union find algorithm. So n over here is the stone count. Each stone is identified by its index in the input list. So stone 0 is stones of 0. Then parent list of range of n, which is length of stones. It gives 0, 1, 2, all the way up to n minus 1. So this means that every stone starts as its own parent. Then rank is 0 of n, so it stores an upper bound on the height of the tree rooted at each node. Then this is the classic find function. So this returns the root of x's component, which serves as the component's ID. Now the loop condition is that if parent of x is not equal to x, it says that x is not a root, keep climbing. And when it falls, x is its own root and we return it. Then parent of x equals to parent of parent of x is path halving. So it repoints x at its grandparent, and it skips one level. Then x equals to parent of x. So it moves up to that grandparent. So each iteration climbs 2 levels while flattening one link. And repeated find calls on the same region progressively collapses the tree towards a flat star, which is why later lookups get cheap. Then is the classic union algorithm. So what this part is doing, it resolves both nodes to their roots. If the roots match, A and B are already in the same component and there is nothing to merge, returning early, and it also prevents a node from being made its own parent's child, because that will create a self loop. Then if rank of RA is less than rank of RB, this part we are doing a swap over here. So the swap guarantees RA is the root with rank at least as large as RB's. So then parent of RB is equal to RA, which means it hangs the shorter tree under the taller one. And that direction is the whole point. So attaching shorter under the tall leaves, it gives the combined height unchanged. And if rank of RA is equal to rank of RB, so this one case where height actually grows, that is when both the trees, they have the same height. So whichever root now sits one level below the other, the merged tree has height of +1. So that's what we are doing. And then this is building the graph. So for I in the range of n, for j in the range of I +1 all the way up to n, but this is not inclusive. So every unordered pair of stones is tested once. So j starts at I +1, so you never compare a stone to itself or repeat a pair in reverse. Now, stone of I of 0 is the row, and stones I1 is the column. So the condition is same row or same column. Now, each match unions the two stones into one component. So if A shares a row with B, B shares a column with C, then A and C land in the same component, even though the loop level never found them directly compatible. You run your union function. And then the answer. Now, this is a set comprehension. It calls find on every stone and collects the distinct roots. So one root per connected component. So length of this is the component count. Now, unlike the row column node version, in this version, every index corresponds to a real stone, so there are no singletons to worry about. And yes, we are also subtracting from n because this encodes the core side that within any component you can remove all but one stone.